So this work comes out of an observation that sort of looked at what we were doing in the Pi SVM and then noticed something that we had missed, which is that when you're playing with RBF SVMs, and so this is true only for radial basis functions with a few extra properties, because the radial basis function decays so fast, right? So your Gaussian, depending on what sigma is, they decay very fast as you're leaving. So if here's our data, we have three things: a blue class on the outside, red and green on the inside. As I get away from that, the kernel's functions decay very quickly. So if I build a one versus rest classifier for each of the red, green, and blue classes, you'll see that the green class and the red class in this case actually have compact support. The plane here is below 0, so if I chop this off at 0, I get a small little circle around the red region. The same is true for the green, but the overall classifier does not have compact support because the blue region takes over all of space. Okay? And this turns out to be true. In fact, for a binary RBF SVM, one of them always takes over infinite space, the other may or may not. For a general N class, some of them will and some of them won't. And what they recognize is that in fact the decay function, which it sort of was apparent in what I showed before and when we were looking at the binary SVM, this is decaying to a constant. It turns out that the constant it's decaying to is B, the bias in your SVM. Because if you think about what that sum is, you have the sum of a bunch of kernels that are all going to 0 exponentially fast, plus a bias, right? So if I think of the positive side of that, if the bias is positive, then my function decays to a positive value and it's greater than 0 everywhere. So here's a nice simple observation. Don't let the bias be positive. Well, that's not as trivial as it sounds, but what they came up with this idea in the specialized support vector machine is they're going to do a grid search over possible biases to make sure that they're going to force the bias to be negative. And actually they're going to now do a trace. So the SVM tells you the support vectors and it tells you what's the optimal bias. But you can change the bias. In fact, there's been other algorithms that have messed with the bias to trade off in various ways. So they do a grid search, and it's important here that they're going to do an open set grid search. Because if you do the closed set grid search, you will end up with the original bias. So the idea of an open set grid search, which is a variation on what we call cross-class calibration in one of our other papers, is you do your training where, let's say I have 10 classes, you pretend that you don't know 4 of them, you do your training on 6, and then you test on 10. You do that for a couple of mixes in the cross-validation sense, and that gives you a way of testing for seeing unknowns. And if you do this idea of open set grid search, you can then choose a bias that is negative and allows you to maximize your accuracy while also having your bias be negative, so you have bounded open set space. So I won't go into a lot of details. This paper is available in archive and it's still very new. But just as a comparison, again, this is what we call a 4 Gauss data set. It's got blue, green, red, and yellow over here. Give you some intuition what happens with different kinds of things. So if I take a standard SVM and I break this up with Gaussian kernels, right? So a CSVM, I get soft margins, but I get these classes and they extend on forever, right? They're down here, it's still red, and green is way up here. Here's another one where I now have changed the parameters of the SVM. I still get 2 of these being infinite, but one of them is now bounded. If I do a 1 class SVM, these are 2 different versions of the 1 class SVM, depending on if I assume closed or open set for calibration. That's what the C here and the O here is. If I optimize my hyperparameters using closed set calibration or open set calibration. So the 1 class SVM, again, as we see before, it over specializes, tends to not fit very well. Doesn't help it much if I do it in an open set testing. The DBC, I can't remember how to expand it, but this is one of those SVM algorithms that adjusts its parameters. I can't remember what the name of the algorithm. Yeah, decision boundary carving. Yeah. Although this is the kernel version, so they're just charging the bias in a related way. This is the 1V set machine, the thing we described before with the slabs. The slabs, so this is the extension that we released I think a 1.5 years ago. Instead of just saying plus or minus 1, we did a simple calibration. So it can tell you the most likely class, which is based on distance from the slab boundaries, which gives you these weird shapes. So here, there's a blue slab running through here and a green slab running through here. And when the 2 slabs cross over, it's trying to choose the most likely class, which it does by choosing which boundary it's closest to. And then here's the WSVM, the algorithm Walter just described, and you can sort of see this gives you three nice little compact regions, okay? And the SSVM trained on closed and open set gives you much more refined little pieces. And whether or not this is more a better fit depends on how you want to measure stuff, right? Here we have clearly extended outside. I don't know if you can see them, but there's sort of a yellow dots, and then there's a gap of yellow, right? Green dots and a gap of green. So this is generalized. This is much tighter fitting, and for open set, yeah. So the SSFM gives you this. But one of the things I really liked about this is this nice idea that really RBF SVMs have actually maybe done very well for lots of people, because for many of the classes, they are already doing open set, because if their bias term is negative, they're an open set classifier, right? So that's a really cool observation that they made, making use of how to do that. So now let's talk about how we're going to evaluate these things. So first of all, we really don't want to use accuracy. The traditional definition of accuracy, 2 positives, 2 negatives divided by positive, negative, false, positive, false, negatives. And if I have a case where I have 1 in 100 true positives correct, but almost 10,000, there should be 1 minus out of these, right? True negatives correct, right? If I basically are doing something like a detector where I have a sliding window and almost none of these windows have a face in it, and only every now and then do I find a face for a pedestrian, then I've got tons and tons of true negatives. My accuracy can be 99% correct by just saying no every time. This is the trivial classifier, and you don't want that. So accuracy alone can't be very useful. So we believe that for open set problems, F measure is a much more useful statistic, where we look at 2 times precision times recall divided by precision plus recall. And now you have to do well on both precision and recall. And this is actually sometimes called the F1 measure, because these are balanced. There's a beta you can put out here. And any one of those F beta measures would be fine, because they're going to force you to have a balance between precision and recall. But you can't have 0 precision and have a very meaningful system where we want to go. So how do you do open set recognition testing then? Well, one of the ways we can do it is by sort of looking at data sets. So in this case, we're going to do some cross data set methodology. So we're going to do training on just Caltech. And then for testing, we're going to use Caltech plus some things from ImageNet that weren't in Caltech, plus some things in ImageNet that were in Caltech, because they're known classes, but they're different, plus a whole bunch of unknown classes that exist in ImageNet that weren't there. So this is from one of our earlier papers. We had an open universe of 88 classes. So that's the total things we know about. We're going to train with 1 positive class and test with, 1 positive and n negative classes. And then we're going to test with all 87 negative classes during testing. Then we have another one where we did an open universe where we had 212 classes with 1 positive and n, and we're going to vary n, and then test with all of them. So in our open set testing, we used all of the things we know about, but in training, we're going to see a small subset. So we're simulating the unknowns. We actually test with them, but we have to simulate with them. So we're going to look at a couple of different types of feature sets. So in this, we're going to use, this is pre-DeepNet days, right? So we didn't have deep features yet. We used Hog features and LBP-like features, which are based on ours with Grab. It's a multi-scale version of it. So we use those 2 features, we put them together, and then we use a couple of different machines. So we can look at the first version was the linear version, so it would be a 1B set machine versus some typical SVMs. So, and here in this table here, we're showing a paired two-tailed paired t-test of was one algorithm significantly better than another. So this here says that the binary linear was significantly better than the significantly 1B set, significantly significant. So this row, binary 1B set with Hog, was significantly better than binary linear and better than binary RBF, better than the 1 class 1B set, better than the 1 class linear, and better than the 1 class RBF. Right? So those double stars mean that this algorithm outperformed all those algorithms at a statistically significant level of 0.01. And if it's just 1 star, it's 0.05. And then the baseline machine we compared it to would be where there's 2 pluses, which is here. Right? So all of those. So statistically, this 1V set machine on this data set was significantly better than almost everything we compared it with. Okay, it wasn't always better than a binary 1V set machine, right? So we had, if we're comparing a binary, sorry, a one class binary 1V set machine, that's the same thing, but a binary linear isn't much better. And then we have down here with different feature sets, the same kinds of comparisons. If we were to look at the sort of performance over classes, is there a performance difference? So here we have, these are 25 of the classes, so there's things like bathtub and hot tub and I don't know, I can't read them all over here, tripod. And these are sorted in terms of the accuracy of the 1V set machine, which is why this curve is constantly going down. These others are showing sort of how much better it was on particular classes. So the red line here, I can't read any of these, binary SVM with a linear kernel. The blue is the 1V set machine. The purple is the one class, and the yellowish, greenish is a one class 1V set machine. So although we can build a 1V set machine with one class, you can sort of see its performance isn't much better than one class overall. But for the binary machine, the one class was significantly better on almost every category we looked at here. Okay. If we look at accuracy, so this, by the way, was F measure, the plots I was showing. If we really want to look at accuracy, just because people always ask to see, well, what really does happen with accuracy? On accuracy, you'll notice that almost all of their accuracies are better. 1V set machine still does better on accuracies, and we're not trying to not show it because we don't do well. We just don't think it's the right measure. And the one class does better on accuracy because it can reject lots of stuff. Right? It overfits and it can't get very far. So here's another set where we looked at this now as a function of changing the openness. As we change the number of unknowns we get to use during training and testing, we can increase the openness, and we can see that the 1V set machine starts off higher and goes down a little bit. The binary SVM with linear kernel also decays. So all three of these perform relatively flat. We're at a very high level of openness. And so their performance doesn't vary a lot with openness. If we'd actually gone all the way down towards zero openness, we'd see a very sharp drop off, and then they just sort of flatten out. And they flatten out with 1V set above binary above one class. Walter, when he talked about the 1V set algorithm, talked about the sort of idea of pressures on one side of the plane and another. Important to understand how much that changes things. So as I change the pressures, we can sort of see there's an impact on an F measure. It's going from 0.18 down, but it's a moderate performance until you get to very large levels of pressures. In both cases, pressure's a variable you can mess with, but you don't have to mess with it too much because it's pretty flat over a large region, so it's not something you have to spend a lot of time optimizing. Yeah, so if, right, so the top plane, and you can sort of see that the top plane is pretty flat for a while, and then it just drops off. In fact, if we kept going, it drops off down here. Right? So this shows that the back plane really does make a difference. It's pretty insensitive for a while, but then if you keep going, which is the equivalent of not having a back plane, you start really losing F measure, and actually it turns out accuracy as well. You start misclassifying things in that sense. So the next kind of problem we're going to look at is in terms of a problem. Is this going back? No, we're doing fingerprints. Okay. In terms of looking at biometric verification, so we want to answer the question. Oops, this way. Laser. We want to answer: is this new sample matching our sample? So we're looking sort of, is it verified or not? And this comes back down to the idea of the score distributions, which I took a little bit when we did meta recognition. So if we look at this set of scores, we have the false non-match and the false match. This is where the two curves overlap given a decision threshold. I'm then needing to decide it's a false match or a false non-match. And so we want to be able to look at this and figure out how we're going to do this. Well, we can take this data and build our distribution of scores, so very much like we do for meta recognition. And now we can ask, if I want to do recognition, I have build a class for match, class for non-match, and now ask how well it's going to do when we start showing it people very different from our training set. So here we train with label faces in the wild. We have some genuine pairs and some genuine imposters. right? So we have one pair and a bunch of imposters. And in this case, we're trying to do identification. So our gallery consists of 12 people that had at least 50 images. The traditional LFW, you just did matched, non-matched. Now we want to do identification in that category. So our imposter class has the 82 other people at LFW that had at least this many images. So we have a whole bunch of test images that are going to be then finally tested, where we train on only a subset of LFW for identification, and we have our LBP and Gabor-like features that we're going to use. We're going to put those all together and look at sort of what happens for our open set face recognition elements. So if we look at our F measure for accuracy, the two top lines here are the binary one versus set machine with Gabor-like features, and the binary one versus set machine with LBP features, and then binary regular SVMs are these. So as I have my openness, if I train these in a closed set setting, the difference between SVM and 1B set is actually pretty minimal. So it's not going to make a huge difference, coming back to the question you asked before. Right? In a closed set setting, if that's the measure you use, these algorithms might be a little bit better, but not much, because they're not really, that's what they're focused on. But as we start opening the problem and we start testing it, where I give it somebody to recognize it's from a completely different class, even if I let the SVM do thresholding, its performance drops precipitously, where the 1B set machine does a much better job. Now, realistically, even though I've shown you this for 1B set machine, we really want to look at better algorithms than that. So let's go back and look at our Pi SVM. So here's this is going back to the Caltech experiments, where here is one of these should be the 1B set machine is, what? Yeah, 1B set here is purple. Oh, 1B set is orange. So here's 1B set, which we said before was the better algorithm. We actually included more comparisons in this because people wanted to see other kinds of things. So we have one versus rest SVMs with RBF thresholding and multi-attribute space. So using our multi-attribute space SVM normalization, what difference does that make? But here was the 1B set machine, which was the best algorithm we had until this time. We added the Pi SVM. We get a significant boost in our F measure, and oddly enough, it actually increased a little bit as the openness increased, and that's just minor variations as it's playing with the thresholds. Actually, don't know what's the difference between these two slides. So, oh, okay. Oh, yeah. So the difference is scale. That's what it is. So people want to. So if you want to know where the one class FVM, it's so much farther down. It's all down here all by itself. So. Another data set we looked at, which is relatively common for us to use, is the letter data set, which has got 26 letters, sort of in this light, but in the letter space. So here again, we have the ability to synthetically generate various amounts of openness. So if we trained on 15 letters and tested on 16, 17, 18, 19, up to 26, we can vary how much openness we get. And here we have a collection of different algorithms. So we have some very classic things like logistic regression, which people would think should be able to reject things it doesn't know. Our one versus rest normal SVM is in here. We have pairwise multi-class SVMs, and our Pi SVM is way up here. So again, the Pi SVM does pretty good, maintains much higher levels of performance as we vary it. And again, if you want to add the one class, it's so far down here, it's not funny. It's, you know, the other plots are all mixed together. It's way down here, much lower score. So while one class is able to reject a lot of stuff, it starts so far down that it just can't ever catch up, right? It actually is pretty flat. It's much flatter than anything except for the Pi SVM, but it starts at such a disadvantage it can't catch up to anything. Okay, now I don't know what. Just to show you, if you want to look at accuracy instead of F measure, then things are a little bit, one class does a little bit better because it actually rejects a lot of stuff. As we get to a high openness, it's just rejecting a lot of stuff, but accuracy is not the right measure. We just stick it in there for when people are looking for it. Another question, since we're dealing with letters, you could ask, well, what happens if my domain had different frequencies of occurrence? So if we use a reference corpus and ask, well, maybe it's the one class we're rejecting things are just really unlikely. The performance in terms of S measure, again, the Pi SVM does much better. The one versus rest with multi-class thresholding does better than it did before because there was there's a frequency effect, but it isn't very large. The next algorithm to look at is the WSVM. So we sort of showed you where the one reset machine is. And here's the WSVM is actually now the better performing algorithm. Don't we have one of these with the PySVM on it? Okay, so the PySVM was down here, so it's not actually on the plot, but it was down here a little bit. So the WSVM improved the performance over that. The same is actually true when we look at the letter benchmark. So the PySVM, not on here? Okay. The WSVM is actually a pair of algorithms. One of the questions Walter mentioned that we use for the WSVM, our default is to actually use the knowledge of openness. So how many unknowns can I expect to see? Then we get this blue lines performance. If I have to just choose a fixed threshold for how many unknowns will I see, here we have an openness the threshold set of 0.1. Then we don't do quite as well in the closed setting, but we continue to do very well in the open setting. We can mix those two together. In this case, we also wanted to show, like some of the other algorithms we mentioned, so the nearest neighbor plus cap, or the multi-attribute space algorithm plus cap, they perform better than their counterparts. So here is straight nearest neighbor. Here's nearest neighbor plus cap, showing that the cap model really does make things better. Here's multi-attribute spaces. Here's multi-attribute spaces plus cap. So the cap makes it do better in the open set setting, but the algorithms still just aren't as competitive because they're a very weak open set model.